this video we're going to go over how to solve systems of ODEs using the backward Euler. So I've made a previous video on how to arrange higher order ODEs into a system of first order ODEs, and also you need to know about matrices, multiplication for this as well. So if we start with this example, so we have y1 equals y, y2 equals the first differential, and y3 is y2, the differential of y2, which equals y, the second derivative, which also equals, if we move this portion to the right, minus 2 y2 minus 3y. So in matrix form we have y1 and y2, so their derivatives. So the derivative of y1 is y2, and the derivative of y2 we're given in the example equation. So we have minus 2y2 minus 3y1, and as for initial conditions we're given them as well. So y1 and y2 at 1, and that is 1 and 0. So now we're going to find out the matrix of A, which needs this portion. So we're going to rearrange and take out y1 and y2. This is where you need the matrix multiplication. So it would be 0, 1, minus 3, minus 2. Yep. So this is A, the matrix that we need up here. So using the equation we have up there, we are going to figure out y1, so I mean y1.1. So y1.1 equals the identity matrix minus 0.1, which is the step size, multiplied by A, and that's all to the minus 1, so that means the inverse of this whole thing, and that's multiplied by the initial conditions, which are 1, 0. So now what we need to do is find the matrix of the inside of this bracket to find the inverse. So it's also equal to 1, if we do two steps in 1 minus 0.1 times 0, which is 0, so that gives us 1, 0 minus 0.1 times 1, so that will give us minus 0.1, 0 minus 0.1 times minus 3, so that will give us 0.3, because minus minus cancel, and then a 1 plus 0.2, because you've got minus and minus again. That gives us 1.2, so we need to find the inverse of this, and of course we're still multiplying by 1, 0. So to find the inverse, that's also in the matrix video I've done previously. So I'm just going to continue y.1.1. So the inverse would be 1 over the determinant, which is 1.2 minus negative 0.1 times 0.3, 1.23. And then we swap these two and negate these two. So we have 1.2, 0.1, negative 0.3, and 1. So once we found the inverse, we're still multiplying by 1, 0. So once we do the multiplications across, we are left with 1 over 1.23 multiplied by 1.2 and 0.3. So we could multiply because it's scalar, but because we need to do another iteration, because we need to get to 1.2, we'll just leave it like this. So y 1.2, so we need the same formula. 1, 0, 0, 1 minus 0.1 multiplied by 0, 1 minus 3 minus 2. We're still using all the same numbers, except from here where we use this value. So 1 over 1.23 multiplied by 1.2 and negative 0.3. So because this portion is the same as what we've done previously, we can just skip straight to here. So we have 1.2 equals 1, 0.1, 0.3 and 1.2 to the inverse, but we're multiplying by 1 over 1.23, our previous value. So we already worked out the inverse here. We can see it's 1 over 1.23, and we have a 1 over 1.23 here. So this will be 1 over 1.23 squared, and we're still multiplied by this 1.2, 0.1, negative 0.3 and 1, and we've still got this. Feel free to watch the video again in case some things are a bit confusing, but we have this. So we just need to multiply across to find the next iterative step. So if we multiply the matrices first, we'll get 1.2 multiplied by negative 0.3 plus, sorry, the wrong one. So 1.2 times 1.2 plus 1.1 times minus 0.3, and then we would have negative 0.3 times 1.2 plus 1 times 0.3, negative 0.3. So we'll get y 1.2 equals 1 over 1.23 squared, and in that bracket, if we added everything, we would have 1.41 and negative 0.66. So to get y 1.2, because we mentioned here that the upper of the two in the matrix is y1 and y1 is y, so to get y 1.2 we'd need to find 1.4 multiplied by this scalar. So y 1.2 is 1 over 1.23 squared multiplied by 1.41, which gives us 0.932 to 3 significant figures. So that's how you solve systems of ODEs using the backward Euler method.